Hi, and welcome to the lab for Module 2 on logistic regression with MNIST data. This lab is divided into two notebooks, 103A, which does the data download and writing to a local file, and 103B, which actually builds the logistic regression model. So we'll start with 103A. Now, for both these notebooks, since they're the first notebook for the course, I'm going to go through each line of code just so we can try and understand everything we see. And subsequent labs will go much faster. So this first section here is bringing in the libraries we need. There's matplotlib, numpy, os, sys, and then here we do a little try except to try and find the URL lib in one of two places, and that's just because there are different versions of it. And then this line right here with the % is a directive to the Python notebook saying for the matplotlib plots that we create, make them inline in the output pane as opposed to a floating window. And that makes them much easier for us to manage. Okay, the first thing we're going to do is the data download. And for that we have three functions defined here, load data, load labels, and then a try download that calls both of them. So let's walk through and see what these are doing. The load data starts with printing, downloading, and src, which is the URL of the file we want to download. Then we use this library routine called URL retrieve to do the actual download from the src source file, and we put it in a local file called delete me, so we can remember to delete it if we see it laying around later. Once that download is finished, we print done, and then we enter this try finally block. Inside here, the first thing we do is we open the file with a gzip because it's a zip file. We use gzfname, which is the file name that was created when we created this delete me file. And we're going to refer to that object as gz. The next thing we do is we unpack 4 bytes. This gz read of 4 gives us the first 4 bytes of the file. And we convert that to an integer, and we store it in n. And it says read magic number. So we're going to check if the first element in n, if it's not equal to this magic number for zip files, then we're going to raise an exception saying this is not a valid zip file. The next step, we're going to read in the number of entries that were specified up here as cm, which is the count of images. And so we read the next 4 bytes as a big Endian byte order is called big Endian in this case, into n again. And if they're not equal, then something's wrong and we print out another exception error. Otherwise, we read the next 4 bytes into crow, which is our count of rows, and the next 4 bytes into ccol, which is our count of columns. And for this file, as we understand it, those should both be 28. So we say, if either one is not 28, then we raise another exception. If we pass all those tests, then we can actually read the data. And so here we have a gz read, and the number of bytes to read is going to be the number of images times the number of rows times the number of columns. So we're going to get all the image data out in a very long array. And we'll store that in res, our result. And then finally, we will remove the delete me file that we created here. And right now, all our data is in this res array. And the last thing we do before returning is we reshape it such that it's a collection of cimg rows, which in our case will be 60,000, and then times an array, which is 28 by 28. So that was for the loading the data. Now let's look at loading the labels. It's going to have a similar pattern. we'll see a downloading message. Here's the URL retrieved to download the source file again. Again, we're using it, delete me as the file name. And we come with gzip.open again, and we're going to unpack the first 4 bytes. That's our magic number. If they don't match, we raise an exception. We get the next 4 bytes, store it in N, and if that's not equal to the count of images, then something's wrong with the label file also. And now, here's where we read the labels. The number of bytes we want to read is CM, which is the count of images, and the reason that it's exactly that is because each label is stored in a single byte. So we store that in our res variable. We remove the temporary file, and then we reshape this as C image rows by 1. So we have that array is returned. And then down here we have the try download function where we give it the data source, that's the URL to the data, and the label source, the URL to the label, and the count of images. And we just call each of these functions we just went through. Load data and load labels. And we store it in data and labels. And then we use NumPy HStack to merge them horizontally into a single array of data and labels. So what we're going to get out of this is something that's 60,000 rows and 28 by 28 is 784 plus 1 byte for the label should be 785. So that should be the shape of the data that comes out of here. So let's go down here to the next section. Here's where we set up all the URLs. So here's our images for training, our labels for training, and the number of samples is going to be 60,000. That's the number of images and labels. And here we actually call the try download to download them, and we store that in train. And then we do the same thing for the test images and labels. And the number of those is going to be 10,000, and we download those into test. So I'm actually going to, I haven't run this yet, so I'm going to hit Control-Enter on the first code block, and those are all functions, so we don't see an output. Now I'm also going to run this with Control-Enter, and we can see the output starting down here. It's downloading the training images, training labels, and there they are, all done. If we wanted to test the shape of these, we can just insert a little cell here and say np.shape of, let's say, train. And I'm going to predict that's going to be, well, here. That's right, 60,000 by 785. And if we do the test, it should be 10,000 by 785. There we go. All right, so that's what we expect. Here's a little bit of code to visualize one of the digits. So we're going to pick at random here sample 5001. We're going to use Matplotlib's IMShow to plot the data as an image. We'll turn off our axes. And here's our sample number coming from our training data. Everything but the last byte, because that last byte is our label. And we reshape it to 28 by 28, which is what IMShow wants. And we're going to use a gray scale mapping. And then we'll also have a little print statement saying what the label is, using the -1 to get the byte at the end. So let's run that. And there we go. So it looks like a 3, and the label for it is 3. So that's a good sanity check. Now that we've got the data in memory, we want to write it to a local disk file. And we also want to use a particular format that CNTK prefers, which is CTF, their CNTK text format. And what that looks like is essentially, if you can see here, there's a vertical bar, labels, and then the label data followed by a vertical bar, features, then the feature data. And so you'll see that for each line in the text file that we're going to create. So let's walk through what this code does, how it does it. First of all, let's review one hot encoding. So we're going to, right now our labels are stored in a single byte, and we want to expand those to a one hot label. So in this case 0, 1, 2, 3, if our label is 3, we'd want to output a one hot label that looks like this. So let's see how that's done in the code here. We call this save text, we give it a file name and the array of the data. We extract the directory name from the file name and make sure that it exists. If it doesn't exist, we create it. And if we don't already have the file, then we go through this code. Otherwise, we can just say file already exists. So here we say print saving, the name of the file. We open the file name. W says open it with write, and we store the file object in F. And then here's kind of a tricky part. So we're calling this NPI, which makes a matrix with diagonal ones. I'll show you how this works. To understand this a little better, let's insert a cell at the bottom that we can play around with. So if I just copy and paste this part of it, bring it down here, there we go. And if I run that, we'll see what we get is a 10 by 10 matrix with ones in the diagonal. And if you think about it, each row here is a potential one hot label. This would be for 0, this would be for 1, this would be for 2 and 3 and 4 and so on. So all we have to do is use our byte label to index into this array and take the corresponding row of values there, and that'll be our one hot label. So we store that in labels, and then we go through every row in our data array. We convert the row to a string, and then we take this labels array, which is down here, this is our big 10 by 10 matrix, and we index it by row of -1. And the -1 is the last entry in that row, which is our label byte. And so this will give us one of these arrays for a one hot label, and we'll store that in label stir. And then we'll take our row value up to -1, and we'll store that in feature stir. And then we actually do the write to our F file, which is our text file that we're saving to. And we'll put the vertical bar labels, and then we'll call for an entry from our list here, which will be our label stir. And then we'll do vertical bar features and call for an entry for our features. So let's go ahead and run this and see what it looks like. Actually, that's the definition of the function. We have to come down here to see it run. So we're going to do some more stuff with paths. We're just trying to figure out here, by doing these path joins, it joins all these path parts together in one path. And so we're looking for, the MNIST data can be one of two places. We have examples and tutorials in CNTK. So we're first checking to see if it's in the examples. And if it's not, then we look inside the tutorials directory. And once we have our data, we actually save the text to that directory using that the directory and file name specified here from the data train. And likewise, we join the directory with this file name for the test, CNTK, train and test. And then our train and test data, and then it says done. So let's run this. And it happens very quickly. And now that that's done, let's go and check and see what our output file looks like. This is our directory we wrote it to. So if we look here, we can see the first line starts with the vertical bar labels, and then we have a one-hot encoding. Looks like 0, 1, 2, 3, 4, 5. This is the digit for 5. Then here's our features, and we should have 784 values till we get to the next line where the next labels is, and that represents our image. And then it continues on with the next line, a new set of one-hot encodings and a new set of values for the image, and so on and so on. For, in this case, this is the training, so that would be for all 60,000 image label pairs. Okay, that completes this lab. I encourage you to go through the lab yourself, try and poke around, make sure you understand what's going on, and you can also try some of the suggested exercises at the end.